Hello students, welcome to all aspiring engineers in my YouTube channel presented by Professor Priya Shimpi. In this video, we are going to study about Zener diode. These are the contents. We have to study the Zener diode construction, its type of biasing, related the characteristics, forward characteristics and the reverse characteristics, and the complete VI characteristics, and yes, the list of formulas which is very important for your online exams. See here, how the Zener diode is made. The Zener diode is made by using PN junction semiconductor diode, right? So, a scientist named as Zener, he has done some experiments. He has taken the normal PN junction diode and he doped the normal diode very heavily. And the resulting diode and a resulting behavior of such diode it came, and this diode they named after the scientist as Zener diode. Okay, so this is a special type of PN junction semiconductor diode in which these semiconductors are heavily doped, right? And what is the speciality is? The speciality of the Zener diode is its reverse breakdown voltage we can adjust between 3 volts to 200 volts. Between 3 to 200 volts we can adjust the reverse breakdown voltage. So that means my Zener will not get damaged till 200 volts. Okay. So how to draw the symbol of the Zener diode in the circuits? If you see, the symbol of Zener diode is very much similar to the normal PN junction diode. The Zener diode also has the two terminals named as anode and cathode. This side it shows your p-type semiconductor. This one is from this side it shows the n-type semiconductor. But how to differentiate a normal diode and your Zener diode? So that is how, if you see the cathode terminal, we made it something like zigzag, right? It very resembles the shape of Z, and that will denote in the circuits, yes, it is my Zener diode. Now, biasing the Zener diode. What do you mean by biasing is the process of applying external voltage to any component. Simply, if you connect a battery to any given electronic component, the process we call it as a biasing. So, Zener diode can also be biased. Yes, Zener can also be forward bias. Zener can also be reversed bias. But when we make Zener a forward bias, its behavior is very much similar to a normal PN junction diode. And here is the speciality of your Zener diode. When it is made reverse bias, and now it acts as voltage regulator, right? And why it acts as a voltage regulator, we have to cover this point. Let us first see the VI characteristics of a Zener diode. These are divided into two parts, forward characteristics and the reverse characteristics. So when we make the diode is forward bias, the behavior we draw on a graph called as forward characteristics. So how to do the forward biasing of a Zener? You know that this is a cathode terminal, this is negative, below one is positive. You have connected the Zener to this. This one is your external voltage. You may call it as a battery. And the battery has the two terminals. The shorter terminal is negative and the longer terminal is your positive terminal. So how this external is connected? External voltage is connected to your Zener. See that we are making it forward bias. That means negative of the battery, it is connected through the resistance the negative of the battery, it is connected to the negative of the Zener diode. The negative, yes, your Zener diode has become forward bias. So when the Zener is very much forward bias, I am saying its behavior is very much similar to normal PN junction diode. So that means this forward characteristics of Zener, the curve will also looks like to be, it will be very much similar to your PN junction diode. So how to read this graph is, the Zener will allow the current in forward direction when the battery voltage is greater than barrier potential, that is 0.7 for silicon and 0.3 for germanium. Then only the Zener will allow the current to flow in a forward direction, isn't it? Now let's see the reverse biasing of a diode. What will happen if we make the Zener to be reverse bias? How to make the Zener to be reverse bias? Now see here, again the direction of the Zener is the same. Here one is the negative terminal of Zener. Here is the positive terminal of the Zener, right? And now see this external voltage. See it very carefully. The external voltage, we have changed this direction. Now here we have kept its positive terminal and below is the negative terminal. We have changed its direction in order to make the Zener to be reverse bias. So the positive terminal of the battery, now we have connected it to the negative terminal of the Zener, and the Zener diode becomes reverse bias. So when the diode is, we have to always say the Zener diode or simply Zener. If we make the Zener to be reverse bias, it shows two breakdown mechanisms. One is Zener breakdown and the second is Avalanche breakdown. Yes, and this is the speciality of your Zener diode only. It has two types of breakdowns when it is reverse bias. Right? So this Zener diode, what do you mean by Zener breakdown? When we are applying the negative voltage or when we are applying the reverse voltage, here is my Zener, we are applying here the reverse voltage, right? So this reverse voltage, right, here the Zener will always have some voltage in it. Okay, when we are applying the reverse voltage between, see here, between 5 to 8 volts, what happens is the voltage in the Zener diode, it remains constant. You apply the reverse voltage in such a way that the voltage in Zener, we call it as Vz, it remains constant irrespective of the change in the current, right? If you see in the Zener breakdown, it is that breakdown in which, see, the change in current, the change in Zener current, what you can observe here is the Zener current has started to flow suddenly and sharply. Right? So there is an abrupt change, a sudden change in the Zener current, right? At a voltage Vz. Though the voltage remains constant, and the current rises sharp. Such a region we called it as Zener region. Right? So you can have this Zener breakdown can be observed with the VZ is less than 5 volts. It is less than 5 volts or 8 volts. It should be between 5 to 8 volts. Within this you can observe the Zener breakdown. So in this curve you can see the voltage across the Zener diode VZ, which remains constant, but current changes. The current changes, it depends on the supply voltage. The supply voltage, that means the reverse voltage. And yes, the VZ remains constant. That means a Zener is always operated as voltage regulator. Mind it, in the Zener region only. That means your Zener diode will give you the constant voltage between 5 to 8 volts. Okay, and that is the speciality of your Zener diode when reversed bias. In the Zener region, it is used as voltage regulator. Now let us see what is this avalanche breakdown. The second type of breakdown, it is your avalanche breakdown, and this breakdown is observed when the VZ is higher than 8 volts. Right? So the VZ is higher than 8 volts. I can say the VZ is greater than 8 volts. Here I can mark this is at 8 volts. Right? So if you see in this particular region, your current has started to rise gradually. The Zener current rise is gradually. So if the current is increasing gradually, can you see this? VZ is no longer constant value. Your VZ has started to change. Right? And this is the region where your Zener diode will get damage. And you cannot use Zener as voltage regulator in avalanche breakdown since it gets damage. So the Zener should never operate in dash region, in avalanche region or in avalanche breakdown. You should never operate. And this is a very important figure. When this avalanche breakdown will observe, when the VZ Zener voltage is higher than 8 volts. Let us see the complete VI characteristics of the Zener diode. So if you see, it is very much similar to your PN junction diode in the quadrant 1, where we have make a Zener diode to be forward bias. A forward voltage is applied and a forward current will flow after the 0.7 volts. I can say after the cut-in voltage, and it will be increasing exponentially. Right? So if we make diode to be reverse bias, you apply the reverse voltage. Though the current is flowing in the reverse direction and that is a sharply and suddenly flowing, this voltage in the Zener, this is the voltage in the Zener, it remains constant. Right? And you can use this property as voltage regulator. Right? So the change in the Zener region, what we have to observe is the change in this Zener region, which is sharply changing. It should be within the limits IZ mean and IZ max, right? If the Zener current increases beyond its maximum value, you start to see the second type of breakdown, that is the avalanche breakdown, in which your VZ has started to change and a point will come where the Zener will get damage. So where the Zener is getting damage, it is of no use, but one must know this fact, right? So that is why we haven't shown here the avalanche breakdown. The useful region is only Zener region, and that is why it is shown on the graph. But being a technical engineer, you must know what will happen if you increase the Zener voltage beyond. If you increase the Zener voltage beyond 8 volts, you must know that Zener will get damage. Now, so we have to see the equivalent circuit of Zener diode, right? How Zener will be replaced in the circuits, right? If I talk about ideal Zener, whenever in the circuits we keep the Zener diode, that means we are giving a constant voltage in the circuit, and that is why the Zener for ideal Zener will be replaced by a voltage that is VZ, right? That means we are giving a constant voltage in circuit. If I talk about the practical Zener diode, right? So the practical Zener diode, along with this VZ, it gives some resistance. It gives some resistance because yes, initially the current was constant and at a voltage VZ, there is a sharp rise in this current. The current is changing. That means yes, there is some change in the resistance of Zener, right? So for practical Zener diode, we replace a resistance along with its Zener voltage VZ. Okay, so this is how you can go through the comparison between Zener and avalanche breakdown. The very first point is very important for your MCQ point of view. The Zener breakdown will always observe between any Zener diode in the universe. It will always observe between 5 to 8 volts, and your avalanche breakdown in a Zener will always observe VZ higher than 8 volts. Now let us say if I have given you VZ is equal to 6 volts. You have to think which breakdown will observed in Zener, whether it will be a Zener breakdown or avalanche breakdown. You have to think on your own. Let's move. These are some applications of Zener diode. Yes, I have told you it is used as a voltage regulator, and voltage regulator, it is a very last step in regulated power supply. We have discussed it earlier. Yeah, and Zener can be used in clipping circuit, clamping circuit, in the protection circuit. Okay, and yes, you are very much familiar with this. Zener is used as a voltage regulator. Then these are some specifications. Zener will dissipate some power in it. You must know the VZ of the Zener diode. You must know the Zener impedance. Impedance is nothing but the resistance, and the maximum IZ max. These are the specialities, one must know its values. Now let us see the power dissipation. These are the two formulas, very important for the online exam. 2 marks numericals. 2 marks numerical based on the simple formula. Power dissipation in Zener diode. Power dissipation, you know the formula for power. It is a product of V into I. Right? We are calculating for Zener, that is I have written here as P suffix Z. Zener diode power dissipation. It is a product of Zener voltage multiplied by Zener maximum Zener we are considering. Always remember, whenever you have to calculate the power dissipation in Zener, we are always considering the maximum Zener current and not only the Zener. Why? Because the Zener diode in the Zener region, it has the two values, IZ minimum and IZ maximum. So always this, its maximum current value we will be considering to calculate its power dissipation. And impedance in Zener diode. Impedance. What is? It is very much similar to, impedance is very much similar to the resistance. Right? If I take the resistance in complex form, that means resistance plus the reactance in the complex form, resistance plus reactance together, this gives me the impedance. Right? So where this reactance is 0, so your impedance is equal to resistance. Right? So here's, for the time being, you can consider impedance is nothing but the resistance in Zener diode. So here is impedance, we always denote as by Z, and we are calculating in Zener diode. It is shown Z of Z. In some of the books, it is shown in R of Z, resistance in Zener diode. Okay. What is the formula for resistance? R is equal to V by I. Right? So the impedance here will be delta, that is the change in VZ divided by change in IZ. When the Zener current is going to change? Yes, when there is a avalanche breakdown. Right? When there is a avalanche breakdown, your current value will be changing, and here your VZ value will be changing, isn't it? So at the time of avalanche breakdown, we are going to calculate the Zener impedance. That means delta VZ divided by delta IZ. Yes, its unit will be ohms. Thank you.